In CFS, the Linux kernel implements two separate priority ranges, two ways to basically manage priority. The first is the nice value, which ranges from -20 to +19 with a default of 0. So when you start a new process, it will almost always start with a priority of 0 unless you change it to start with another priority. And this is mostly used only in CFS. And larger nice values corresponds to more niceness, basically the process being less uh, having less priority than all the other processes, and lower nice values are for much higher priority. So a process having -20 is has much larger priority than a process having +19. The second way to prioritize is called the real-time priority, and this is not really used in the CFS. It's used in the real-time scheduler, as we'll talk in a few hours. Sorry, in a few slides. The values are configurable, both of them basically. The first one, the values are configurable between -20 and +19. The second one has a default range between 0 and 99, but you can change the default range. So maybe you want to start from 1 to 10 or something, and 0 to 99 inclusives. That means that 0 is included and 99 is included. And you can use ps minus eo state uid pid ppid rt prio time com to basically get the priorities. I mean, you can say that rt prio is basically the real time priority, and these will basically describe to you different parts of the process, different properties of the process that you're running. So in CFS, time slicing is that does not depend on constant time. So when we're talking about the MFQ, we said that you might have higher priorities having 10 milliseconds, lower priorities having 70 milliseconds, for example, in the different queues that you had. CFS implements it in a different way. This is the how Linux implements it. You do not assign time slices, so you do not say that the highest priority job will use 10 milliseconds and the lower priority jobs will use a higher number of milliseconds, but you rather assign it using a share of the processor. And that's basically saying that this process should get 20% of the CPU time and the other process should get 80% of the CPU time, and you try to keep that balanced while running them. And this is basically decided using the nice values. So the nice values are used like weight to each process. Otherwise, if you have all of them having niceness of 0, then you'll end up with all processes having 1 over n, where n is the number of processes time on the processor. uh, the Linux scheduler is built upon scheduling classes. This is the concept of scheduling classes. So you have multiple classes that you can configure in your system. One of them is, for example, sched which is basically CFS. One of them is sched which is the scheduling using the real-time scheduler. We'll talk about it in a bit. One of them is sched and that's basically the deadline scheduler, which was, by the way, developed mostly by people in Italy, but to a huge extent by people at Ericsson Research here in Lund. So yes, there are actually a lot of people in Sweden who are working on changes to the Linux scheduler, but Ericsson is one of the major contributors, of course. So, and the way that the Linux scheduler works is that it's modular, so you can use different scheduling classes, and each scheduling class is basically one of these different scheduling algorithms, and then you have priority between these different classes. So, for example, sched which is schedule using using the real-time scheduler, will just give you higher priority when it comes to how your process runs. So sched will any job that has been tagged as sched will run over any job that is tagged as sched normal, which is scheduling using CFS. And these algorithms coexist, and the Linux scheduler, in essence, just manages between the different algorithms. Uh, yeah, and you can actually take a look at the sched class struct defined in sched.h, where basically some hooks are defined, and these hooks define what you should implement to get basically your Linux scheduler, to design and build a new Linux scheduler. I mean, the new Linux scheduling class, of course. The Linux scheduler expects 4, 5, 6 functions to be implemented in your scheduler, in your scheduling class. So if you are implementing a new scheduling class, then what you need to do is basically to implement these 5 functions, and then the Linux scheduler will know from there what is actually how to handle in queuing and dequeuing of jobs, which job runs first, and so on. One thing to note also with the scheduling classes is that of course you will need further more than just implementing the scheduler, to also register the scheduler and give it a priority, saying that this should run higher than, for example, CFS. So if I have jobs that I have designated to run in this using this scheduling class, then they should run before any jobs that are, for example, going to be CFS, but following any jobs that are going to be in real time using the real time scheduler. So, and I've actually thought for the project to, I mean, I thought that one nice project would be to ask you to implement a Linux scheduler, but then I realized that this is probably too much work. So, no. This is actually the code in sched.h. So if you look at the sched.h code, the sched.h file, you will see basically the sched class struct defined such that you define a few functions in queue the queue task, yield task, yield to task, and check preempt car. These are, and yeah, I mean, and a few other tasks, a few other things that you need to also define that are below. And if you look at these are the basic minimum number of functions that the operating system, that the Linux operating system expects from you to implement in order to have an actually working new scheduler. And most of the work is actually not done in. I mean, there's of course some work to be done in this. This is basically your scheduling algorithm, 5 or RR or something, round robin. But there's quite a lot of work that you actually need to do when it comes to plumbing these inside, because you need to handle a lot of other things uh, in your system, and these are the harder than probably just implementing these 5 or 6 functions. This is actually the fair scheduler, the CFS, complete fair scheduler. This is the file fair.c. You'll find it in /kernel /sched /fair.c, and it has a pretty nice description in the documentation, so you can actually read a lot about how it was designed and design decisions that were taken into designing fair.c. In sched.h, you have priority classes that you check basically. If you look at line 1238, you have basically you have a declaration that basically has a for loop that would go through all classes and check what class has the highest priority, and basically based on that class you will pick what jobs to run. And yeah, you have also the definition of the scheduling classes over here. So there is the stop scheduler. This is the lowest this is I think this is the lowest priority scheduler in the whole Linux system. It's called the stop scheduler, and that's, I think, just run very seldom. And then there's the deadline scheduler, the real-time scheduler, the fair scheduler, and the idle scheduler class. And this is, if you remember, we have talked about having an idle thread, and this is basically scheduled using the idle sched class. There are four issues that were identified when they decided that the fair scheduler should not use absolute time times, basically say for each priority for each nice value, like the MFQ is supposed to be in the book. And they have identified four issues with the technique discussed in the book, which is basically having, for example, 10 milliseconds for highest priority and 70 milliseconds for lowest priority, or something like that. And that's for basically, if you go from, for example, suppose that you have basically went you have decided that it's best to implement it the way in your operating system's book, where you had 10, 20, 30, and probably until 70 milliseconds. You, one of the issues that you have is that if you allocate to one process, if you have two processes and you allocate to one of them 10 milliseconds and to the other 20 milliseconds, then you have basically allocated to the second one double the time allocation that you have given to the first one. But if you and that's using just a 10 millisecond time difference, right? And if you have just these two jobs, then one of them will run on, for 1/3 of the time, the other one will run for 2/3 of the time, having double the time. Now, if you go from 60 to 70, you're still allocating extra 10 milliseconds. And if you just have two processes that run on this, one of them having 60 milliseconds allocation time and the other having 70 milliseconds allocation time, that will mean that one of them will get almost 50% of the CPU time, and the other one will get slightly less than, probably something like 45%, and one of them will get 55%. And if you look at this, then this is, I mean, although you have increased the priority or given the same time quota, the same increase in the time quota to your processes, but due to relativeness, they are not equal. The 10 milliseconds are no longer equal. Okay, uh, so that's one of the problems that you have. Uh, there is there are other problems that I mean, it's very hard to actually get a really precise 5 milliseconds on a computer. I mean, the clock speeds vary, for example. So you're you might have heard that about the term overclocking. You might have done overclocking on your system, for example, and the clock is the way that you would calculate the time in the operating system. And since you have these variations in for example, clock speed, then it gets a bit harder to do the very fine-grained time-based allocation. Of course you can, but it adds a lot of complexity in your system. Uh, there is a problem with basically mapping the nice values onto time slices, and the problem is quite simple. What does it mean to be at a priority 0, and what does it mean to be at a priority 19? What you would typically want is that you want something with a priority 19 and something with a priority of minus 20. Nice value, nice priority value, basically, of 19, and one having a nice priority value of minus 20, to have basically relatively, I mean, do you want to have each one of them, for example, should we make the time slot 1 millisecond, and then the difference would be 19 to 20 to minus 20, then the difference would be 40 milliseconds between them. Should we make it 5 seconds? Should we make it 10 seconds? Should we make it 3 seconds or 3 milliseconds? I mean, there is just no way to basically say that this is the correct time slice, and that basically makes it also pretty hard to use such values, because the time slices are just, I mean, it gets pretty complicated to decide on the number of milliseconds that you want per nice value. You can, of course, use, for example, some geometric function to map, for example, so have uh, y equals x squared, for example. So that if you have a priority of 0, you get, for example, 1 millisecond. If you have a priority of well, y equals x squared plus 1 or something. If you have a priority of 1, then you get 2 milliseconds. If you have a priority of 2, a nice value of 2, you get 2 squared plus 1, and that would be 5, and so on. But I mean, it adds a lot of complexity in your system. Uh, and then the last one is, it's hard to handle the process wake up in a priority based scheduler. That if you are trying to optimize for interactive tasks, what you want is that you want to make sure that something that just started would run, because it has never had any time on the CPU processor. And this is doable with time slices, with absolute time slices, but not optimal, because it gets, again, extremely hard to basically, when the process starts, you want an interactive application. I mean, you want, when you fire up your video or something, or when you fire a shot in your Half-Life game, you want it to be interactive, so you want it to run right away. You do not want it to be scheduled later, and then you see the effect like 1 second later, because you just have a lot of processes. And when waking up, it's much easier to basically say that this process has never run, has had 0% of the share of the processor, than to say this process, than to keep track of how long did this process run on the processor. Because you can have a counter that basically says that, okay, I have spent 100 milliseconds on the processor since I started. But then for a very long running process, something like init, for example, then you will have a counter that will overflow eventually, because you'll keep adding the time you run. I ran 10 milliseconds, now I ran 50, after a while I ran 100, and in no time you will overflow a counter using that. So these are the four issues with just using a time slice that is predefined.